So all of 10.6 deals with one type of very specific series called the alternating series. Um, yeah, this is one you're going to recognize it right away. So let's just take a look first before we get into the test for alternating series, what it looks like. We'll start with a series you're all familiar with, right? N equaling 0 to infinity. We have our basic geometric series here. So what does that series look like? Well, it starts with a 1 because anything to the 0 power is 1, plus 1 half plus 1 half squared plus 1 half to the third plus 1 half to the fourth, right? So you get the idea. You know your geometric series, r equals a half. We can easily state what that series does, knowing that r is less than 1, and we can say it converges. Okay, now, what if I make a slight change to this series? Instead of r being a half, it's negative 1 half. How does that change the look of the series? Well, the 0 is still 1. But then to the first power, it's minus a half. Oh, well, the second power squared becomes positive. So you can see anytime you're raising it to an odd power, it has a negative in front of it. This essentially is an alternating series. So again, we know our basic 1 half to the n converges because we said the absolute value of r is less than 1. So it converges. Notice this, by the term definition of a geometric series, totally still converges because the absolute value of r is less than 1. So that doesn't change anything because we know this is still a geometric series. How else could I write this? So let's look at this. Couldn't I write this as negative 1 to the n over 2 to the n? Okay, and this is very often how you will see your alternating series written. I can even do negative 1 to the n, 1 over 2 to the n, right? So an alternating series, as you'll see in a minute, has a kind of this general form of negative 1 to the n of some other series. And that's what we did here. But this is a series, again, we're very familiar with because though it's alternating, it's also a geometric series and it still follows because in a geometric series, we just really need to look at our absolute value. So we don't need to worry so much about this being an alternating series because we can look at it as a geometric. Also, the other thing, we're going to talk a little bit about this section, so we need to also recall something we did called partial sums. So I'm doing a little review before we actually get into our alternating series. So let's use this series to come up with partial sums. And let's remind ourselves what a partial sum is. So we have something we call the sequence of partial sums. So, well, partial sum is capital S. Partial sum 1 is simply the first term. Well, that's just 1. Partial sum 2 is the summation of the first term. So in this case, it's 1 minus 1 half, so it's a half. Partial sum 3 is the summation of the first 3 terms. 1 minus 1 half plus 1 fourth, and we got to do some work here. So we have a half plus a quarter equals 3 fourths. And we're only going to do a couple of them. Partial sum 4 is 1 minus 1 half plus 1 fourth minus 1 eighth. I guess that's 5 eighths. So we can put together our sequence of partial sums. And our sequence of partial sums go 1. Remember, it's a sequence. We're not adding all the sums together. So what is that? That is 1 comma 0.5, 0.75, 625. So what happens is it kind of bounces back and forth. It goes up. So it goes down, goes down. Oh, then it goes up to 0.75, then it goes down to 0.625. And it will keep going up and down these partial sums until it'll actually approach, it will approach a limit that represents, remember, this is geometric. We can find the actual sum. We don't need to worry about partial sums because we can find the full sum. And the full sum of a geometric is just 1 over okay, don't forget your r equals -1/2. So it's 1 over, because a sub n is 1, minus a -1/2 plus 1/2, and it goes to 2/3, which is 4.666. So what'll happen is these numbers, as they keep going, will approach 0.666. So I just wanted to kind of give you a summary of our partial sums. And the reason is that because in this unit, they talk about something called a remainder. And when you're dealing with an alternate series, the remainder is also called the error. Okay. So, for example, if I took S of 4, which I did up here, and I got, my partial sum was 0.625, my remainder, or my error, is actually the summation of everything after that, right? Would be the summation of everything from 5 to n. Okay? It's everything that comes after that added together. Okay? And the idea here of and this was what? -1 to the n times was 1/2 we were working with, right? Yeah, 1/2, 1 over 2 to the n. So that's our remainder, right? And the idea behind it is my sum 5, the remainder for partial sum of 5, whatever that is, which we just said is 5, partial sum 4. Sorry about that. Don't mean to confuse you. The remainder of partial sum 4 is actually written as this. Is going to be less than, that entire remainder is less than whatever a sub 5 actually is. Whatever the fifth term actually is. And we can calculate the fifth term of this series. Okay? So what is a sub 5? A sub 5 of my series is simply -1 to the 5th so it's -1 over 32. I know that sounds crazy, but because I'm showing you with a geometric, we can actually calculate what that error is, right? Because with a geometric, just to prove that this is true, the remainder is going to be 0.625 minus our actual sum, which is approximately 666. And we can just do that math real quick. 0.625 minus 0.666 equals about -0.005. 0.041. Well, we also know that a sub 5 is negative 1 over 32, and 1 divided by 32 is negative 0.03125. So yeah, the error, which would be if we were to add up all the rest of the terms, is less than the next term. So this idea of this remainder is only true for alternating series. So it's brought up in this section very briefly because you're working with geometric, and it's kind of easy to see with the geometric because, again, geometric was the only one we could actually get a sum of. But this is going to come up again in chapter 11. So this is a brief introduction to remainder and error, but you're going to see this again in chapter 11. So you can kind of put it, I guess, to the side for now for yourself, and just understand, oh, this is going to be a part of something we do in chapter 11. But I wanted to show it to you as we're talking about alternating series and talking about looking at geometric. But let's go back to our test for alternating series. Okay, so here we are. The alternating series test. So we've already determined it's pretty easy to determine an alternating series because it has this negative 1 to the n with some series, right? N equaling 1 or 0, whatever, to infinity. Now, an alternating series, sorry about that, I keep hitting the wrong buttons. An alternating series converges if two conditions are met. And these two conditions, the first one is the magnitude of one term is less than the other terms. In other words, a sub 1, the next term is smaller than that. It's kind of got this decreasing. Okay, and these are the actual terms. Okay, don't get this confused when we were doing this sequence up here where we were talking about partial sums. These are the actual terms. But when we do the actual terms, what we're looking at is only the magnitude of the actual term. So you want to think of it as the absolute value. In other words, a half is smaller than 1, a quarter is smaller than a half, an eighth is smaller than a fourth. So theoretically, we're talking about magnitude, so you want to think of these as absolute value. In other words, we're disregarding the negative signs. So as long as the magnitude of those terms are going down. And secondly, the limit of just the a sub n part actually equals 0. So you may recall in a regular series, not an alternating series, we can do a divergence test and we look at the limit of the a sub n term as n goes to infinity. And in that case, we find as long as it's not equal to 0, it diverges, and if it equals 0, it's totally inconclusive. So here's where an alternating series is different. If we just take the a to the n of an alternating series where we know the absolute value of each term keeps decreasing, then yes, if that indeed equals 0, then we can state that it converges. So let's look at an example. Let's take the summation of 1 to infinity of negative 1 to the n of n plus 1 over n. Clearly, here is what designates this as an alternating series. All right. So our alternating series, by definition, the a to the n part now is just the n plus 1 over n. So condition 1, let's just do some terms of our a to the n. We're not concerned about the negative 1 to the n piece. When we do this, we're just looking at the a to the n, or the absolute value of the whole series, we say. All right, well, when n equals 1, I get 1 plus 1 over 2 over 1, I get 2. Okay, that has to be greater than the next term. What's the next term? Well, when I plug in a 2, I get 3/2. Well, so far we're good. And you just want to do a couple of them just to convince yourself. 2, plug in 3, 3 plus 1, I get 4/3, and yeah, you can see where this is going. 4/3 is going to be bigger than 5/4, which is going to be bigger than 6/5, dot, 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 dot. If you're not convinced, just go ahead and get the decimal approximations of each of them real quick, and you'll see that. So check. That's all you need to do. Now let's take the limit of just the a to the n part, n plus 1 over n. So notice, in this case, it equals 0. No, doesn't equal 0. Sorry. I was looking at the second line of my notes. I don't know why I did that. It equals 1, right? The limit equals 1, which is not 0, and it does not converge. And yes, we can say it diverges. Second example. Summation n equaling 1 to infinity of negative 1 to the n over n. Again, with alternating series, it's kind of good to write them out a little bit. Oh, well, you can see right away what's happening here. This is a series we're kind of familiar with. We're starting at 1, so my first term is negative 1. Then it goes plus 1/2 minus 1/3 plus 1/4 minus 1/5. And as you may have guessed by now, we call this the alternating harmonic series. Okay. Number 1, you're comparing 1 greater than 1/2, greater than 1/3, greater than 1/4. Yep, that checks. For 2, the limit as n goes to infinity of 1 over n. We're checking if it equals 0. But remember, because we're dealing with an alternating, not just a regular series, when it equals 0, and this is where it gets tricky because this is very different than your basic divergence test, because it equals 0, we do say it converges. Okay? But here's the trick. And we're going to do an extension. Here's the question you're going to ask when it converges. So when an alternating series converges, and this only happens with alternating series, the question is, does it converge conditionally or absolutely? You've got to further examine any convergence of an alternating series. So, if it converges conditionally, or let me do it this way instead. Here's the deal. If, let's suppose, you have alternating series, right? -1 to the n of a to the n converges. Okay? So we have an alternating series like we just found. We just found our alternating series converges. Now 1. If the non-alternating part of that series also converges, then we say that the summation of -1 to the n, a to the n, converges absolutely. But if the summation of a to the n diverges, then we say the alternating series still converges, because remember, that was the original condition, that the alternating series converges, but it converges conditionally. And by saying it converges conditionally, we're noting, hey, if it wasn't alternating, it would not converge. In number 1, to say an alternating series converges absolutely, we're actually saying even if your series didn't have that alternating part, it still would converge. So now, when we look at the series we just did, which was -1 to the n over n equaling 1 to infinity, we found by the alternating series test that it converges. Okay? But since n equaling 1 to the infinity of just 1 over n, which we all know is the harmonic series, we already know this series diverges, then our original series converges conditionally. All right. So here's the deal. Anytime you are dealing with an alternating series that converges, you have to then check the original series by doing whatever test you want to do, or it might be something as simple as we already know the harmonic diverges, to determine if that series diverges or converges, because then that will help determine if your original alternating series converges conditionally or converges absolutely. All right. Here's the good part. If your original alternating series does not converge, obviously you don't have to do that second piece. Okay. So that's your alternating series. You want to kind of go through all of these series, look over the summary document that I posted, go through your lab, and then when you look at section 10.8, that just kind of puts everything together, and practice your math labs. Okay? And that is the end of your series.